myself student for the CET crash course, the subject chemistry. So I am Pavitra Pai, assistant professor working in AIPM Bhatkar. Okay. Today we will be dealing with one of the important chapters, okay, that has a maximum weightage of marks in KCET, that is coordination compound. Okay. So we'll discuss the synopsis in detail. So whenever you need to solve the questions in the KCET, your synopsis should be very short. It means you have to write the points in such a way that if you once see it, it is understood for you to solve the question. So this is, I'll be explaining the quick synopsis. Okay. So first, when we talk about coordination compounds, first when we talk about compounds, okay, we should understand what is the difference between a normal compound and a coordination compound. Why a specific name, coordination compound, is given to it. So compounds usually will be two types. One is said to be a double salt, and second one is said to be a special type of compound called as coordination compound. So what is the major difference between these two compounds? So double salt, it means the compound that ionizes completely in the solution. What do you mean by complete ionization? For example, take this compound, okay? This is nothing but a Mohr salt. You have used this in your laboratory too. A green color salt, okay? It will be crystalline in nature. That is nothing but a iron-based salt. That is nothing, Mohr salt. So its composition is FeSO4, NH4 twice, that is diammonium, sulfate, 6 hydrate, that is H2O molecule, 6 water molecule. That is a composition of the Mohr salt. Okay, when this Mohr salt is dissolved in water, okay, how the ions comes out in the solution? For example, so in this compound there are individual ions present, right? Iron is present, sulfate is present, ammonium is present, and H2O is present. So when it is dissolved in the solution, all these ions which were in the neutral form comes out as their respective ions. For example, iron, it will come out as Fe2 plus, right? Ferric ion. Similarly, SO4, it will come out as sulfate ion, SO4 2 minus. Ammonium, NH4, it will come out as NH4 plus. Similarly, water will come out as water in the solution. It means all the respective ions, all the individual ions which were in the neutral form, after ionization, it has completely come out as their ion. So no other atom is left behind. Okay, so after dissociation, all the ions have come out in the solution. That is said to be complete ionization. If the salt, okay, or the compound, if it undergoes complete ionization, that is said to be a double salt compound. Okay, that is nothing but a double salt compound. Now, what is then coordination compound? Okay, little bit different from double salt. That is, when a coordination compound is dissolved in a solution, okay, for example, if you take any coordination compound, for example, you will take, okay, potassium ferricyanide. The common name of this compound is potassium ferricyanide. So this is a compound. You have iron in it, you have cyanide ion in it, you have potassium ion in it. When this compound is dissolved in the solution, what happens here? Okay, the potassium will come out as 4K plus, that is 4 potassium ion comes out, that is K plus ion, and FeCN6 as a whole comes out. You see here in a square bracket, you have a central metal ion Fe, 6 cyanide ion, you have written it as whole charge as 3 minus. Okay, so K plus ion you have got, ferricyanide ion you have got. Okay, so there is no complete ionization. Incomplete ion, what should happen? Potassium should come out, iron should come out as Fe2 plus, and cyanide should come out as Cn minus. That is not the case here. So the atoms inside the coordination sphere is intact. They have not dissociated further. So that's why the compounds which does not ionize completely, whereas it ionizes only as one cation and one anion, such compounds is said to be a coordination compound. So that is the major difference between the normal compound, which ionizes completely, that is nothing but a double salt, and second is which ionizes incompletely, that is nothing but a coordination compound. That's why it is said to be a coordination compound. Now, based on, okay, what is the charge acquired by the coordination sphere after dissociation? The coordination compound is classified into 3 major complexes. Okay, one is cationic complex. mean by cationic complex? For example, okay, take this as an example, that is copper, okay, tetraammonium copper sulfate. Okay, this is the example of a coordination compound. When it ionizes, what comes out? Okay, tetraammonium copper acquires a 2+ positive charge and sulfate ion acquires a negative charge. So whatever the molecule is there inside the coordination sphere, it has acquired a positive charge. So that's why this compound is said to be a cationic complex of a coordination compound. By the coordination sphere, whatever it's coming out, it is acquiring a positive charge. That's why it is a cationic complex. Another example is tetraammonium cobalt 3+ complex. Similarly, what is anionic complex? We are taking example of potassium ferricyanide. What we have got, the ions in the coordination sphere has acquired a negative charge in the solution. That's why it is said to be an anionic complex. Whatever the charge will be there on the coordination sphere after dissociation, based on that you name it as either cationic complex or anionic complex. And what is this neutral complex? Example is nickel tetracarbonyl. It does not have any ion outside the coordination sphere. There is no question of dissociation at all. We know that inside the coordination sphere the ions remain intact, they do not dissociate, right? So such complexes which does not have any ion outside the coordination sphere, such complexes is said to be a neutral complex. So cationic complex which acquires a cation charge on the coordination sphere, anionic charge on the coordination sphere is said to be anionic complex, and if there are no ions outside the coordination sphere, such complexes are said to be a neutral complex. Example is nickel tetracarbonate. Okay, so these are the types of coordination compound. Next is, okay, in a coordination compound, okay, you can name each and every part in the coordination compound. For example, we'll take an example of, okay, K4FeCN6, that is potassium tetracyanoferrate. Okay, this is an example. Now, when you see the coordination compound written, there is, first thing you see is some entity is inside the square bracket here, right? Some entity is inside the square bracket here, and some entity is outside the square bracket. Okay, so whatever ions, if it is written inside the square bracket, that space is said to be a coordination sphere. Okay, the contents that are written inside the square bracket, okay, whatever it comes inside the square bracket, that is said to be what? Coordination sphere, where the actual coordination bonding takes place. And the atom that is written outside the square bracket, that is said to be a ionic sphere. So there are two major components in the coordination compound. One is coordination sphere, which comes inside the square bracket, and the entity written outside the square bracket is said to be an ionic sphere. Now, inside this coordination sphere, there are two more written, right? Okay, here there is a cyanide ion, here there is a metal atom. Okay, so the metal atom is said to be a central metal atom, which will come in the center of the molecule, that is central metal ion. And whatever it is written in the smaller brackets, right, common brackets, whatever it is written, that is said to be a ligand. Okay, central metal atom will be sent in the center, and the ligands, here the number is 6, right? There are 6 cyanide ions. The iron atom is surrounded by the 6 cyanide atom. Why is that? I will tell you later. Okay, so inside the coordination sphere, there is a central metal atom and there are ligands. In this case, it is only one ligand. Okay, need not be that only one type of ligand must be present. There are many ligands. So this list may continue. There may be cyanide, there may be chlorine, there may be bromine. So the list continues. So there are different types of ligands. So in the coordination sphere, two major parts is, one is central metal atomic part and second one is ligand part. And the number, whatever, the number of ligands, okay, it will constitute to the coordination number. Need not be every time. If it's a monodentate ligand, you can directly write coordination number as the number of ligands. But if it is a polydentate ligand, you will have formula for it to calculate. Okay, so the number of ligands constitutes the coordination number. Okay, so this is the how you explain the coordination compound. Okay, as a coordination sphere, ionic sphere, central metal atom, and a ligand. Now we will see what is this ligand. I am speaking from that time that is one of the major part of a coordination sphere is ligand. So what is this ligand? Now, a bond must be formed between a central metal atom and the substituent group, right? You can take it as here the cyanide ion is a substituent, okay, which has the potential to donate electron to the central metal ion. So that job is done by the ligand. So ligand is nothing but atoms or molecules, okay, that is linked to the central metal atom, okay. The atoms or molecules that are linked to the central metal atom through a coordination bond. So what is this coordination bond? You know that in covalent bond what happens? Okay, there is a mutual sharing of electrons, right? If there is an atom A and atom B, one electron will be given by atom A to atom B. Similarly, one more electron will be mutually shared by B to A. So that there is a mutual bonding. So that is covalent bonding. But in coordination bond, what happens is one will be electron rich species and one will be electron deficient species. For example, always a metal atom which is in the center, it will be electron deficient species. It means it lacks in electron. Similarly, the ligands that will be surrounding, it is always an electron rich species. Either it will be having a lone pair of electrons or it will be having a negative charge around it. So it is electron rich. So what happens is coordination bond is nothing but the ligand will donate all its extra electron to the central metal atom. It will not receive in return, only it gives away the extra electron. So ligands are nothing but the atoms or molecules, okay, that give away electron and links to the central metal atom through the coordination bond inside the coordination sphere. In other words, ligand are nothing but the electron donating atoms inside the coordination sphere. Since it's an electron donating group, it is always a Lewis basis. You know that Lewis acids and Lewis bases, right? Lewis bases are one which donates, right? Similarly, ligands are also here. It donates the pair of electrons or the negative charge to the central metal atom. Okay, based on how many bonds are formed with the central metal atom. Okay, so one ligand forms how many bonds with the central metal atom. Based on that, the ligands are classified into monodentate, polydentate, okay, monodentate and higher dentate ligands. Okay, based on that, we'll see the classification. So first we'll see what is this monodentate ligand. Okay, the example for monodentate ligands are cyanide, Cn minus, OH minus hydroxyl group, ammonium, okay, ammonium, okay, NH3 and aqua, H2O. This is a monodentate ligand. What do you mean by monodentate ligand? Because in the presence of these ligands, okay, only one donor atom will take part in the coordination bonding, that is donating electrons, okay, to the central atom, metal atom, and only one coordination bond is formed at a time. Okay. Similar, here you can see K4FeCN6, there are 6 cyanide atoms. It means one cyanide atom will form only one bond with the ion. It will not form 2 or 3 bonds, it will form only one bond. So the monodentate ligands are responsible in forming only one coordination bond at a time with the central metal atom. Okay, it may be having more than one donating species inside. For example, here I'll take one more example, nitrate, NO2. Okay, you know that nitrogen also has a lone pair of electrons, oxygen is also having a lone pair of electrons. So there are 2 donating sites. It can form 2 coordination bonds, but no, it's a monodentate ligand. Why it's a monodentate ligand? Because at a time it can form only one coordination bond, either through the oxygen or through the nitrogen. So monodentate ligand is nothing but the ligands which can form only one coordination bond at a time. Next, didentate ligand or bidentate ligand. Okay, example is oxalate. Okay, COO minus, COO minus. It has 2 oxygen donor atoms. So these kinds of ligand form 2 coordination bond at a time. So one oxalate ion can form 2 coordination bond with the central metal atom at a time. One more example is ethylene diamine, that is CH2NH2, CH2NH2. There are 2 nitrogen atoms which is having a lone pair. So those 2 nitrogen atoms takes part in the coordination bond with the central atom, metal atom at once from the 2 nitrogen sides. So 2 coordination bond can be formed at a time. That's why why it is said to be a bidentate ligand. Next is polydentate. Okay, more than 2. Okay, it may be 3, it is said to be tridentate ligand. If it is 4, it is said to be a tetradentate ligand. In general, you can classify it as a polydentate ligand. More than 2 donor atoms. It may be 3, 4, 5, 6. Example is EDTA, that is 6 donor atoms. At a time, it can form 1 ligand, can form 6 coordination bonds with the central atom. EDTA structure will be like this. You know that 4 oxalate ion, okay, CO minus will be there outside, and in between 2 nitrogen from the diamine. Okay, it will be there 2 nitrogen atoms from the lone pair. It can donate also 4 oxygen from the CO minus. It can donate at a time. So 6 donor side, okay, 6 coordination bonds can be formed at a time. That is polydentate ligand. Monodentate ligand, 1 coordination bond. Didentate ligand, 2 coordination bond, and more than 2, anything it's there bond forming, it is generally classified as polydentate ligand. Okay, next is flexidentate ligand. Okay, what is this flexidentate ligand? Okay, no doubt it is a polydentate ligand. It means what? More than, okay, at a time, more than 1 coordination bond or more than 2 coordination bond can be formed. Example is EDTA. Now, for example, EDTA is used as one of the reactant with the central metal atom. For example, you have iron Fe and you have added EDTA. How many bonds can be formed at a time? 6 bonds. But in that system, okay, if only 2 bonds are required for forming, okay, then what happens? It is flexible for the use. Means, okay, as per the requirement of the system, how many bonds needs to be formed, that much is utilized by the particular ligand. So if the system requires only 2 bonds, that means EDTA out of 6 donor atoms will bond with only 2 donor atoms. Similarly, if 3 bonds are required, it will bond with 3 donating sites. Similarly, if the 4 bonds are required by the system, 4 atoms, that is 4 coordination sites, will take part in the reaction. If 6 also, if all the 6 are required, it will form 6 coordination forms. So it is flexible to the use. As per the requirement of the system or as per the requirement of the reaction, it will donate its coordination site. Okay, more than 2, maximum up to 6. That's why it is said to be, since it is flexible in the usage, it is said to be a flexidentate ligand. Okay, next is chelating ligands. For example, diamine. You see that both the nitrogen are parallel and they are close to each other. So it's like a half square, right? It is in the C shape, right? Rectangular C shape. In the square, if you remove one of its sides, that it will acquire. That is the shape of the ethylene diamine structure. So both the nitrogen are close. Okay, you know that it is didentate ligand. At a time, it can form 2 bonds. Okay, one metal atom, okay, 2 of these nitrogen are forming bond with the central metal atom. You can see the structure here, right? You can see the structure here. It acts as a pentagon, right? It acts as a closed structure. So if the closed structure is formed, when a ligand reacts with a central metal atom, if a closed structure is formed, that is said to be a chelating ligand. It means it has the ability to form a closed structure, or the closed structure, in other words, it is said to be a chelating structure. That's why it is said to be a chelating ligand. Okay, so flexidentate ligand and chelating ligand. And last one is ambidentate ligand. Okay, what do you mean by ambidentate ligand? Okay, ambidentate ligand is nothing but a type of a monodentate ligand. What is the definition of a monodentate ligand? Okay, only 1 coordination bond will be formed at a time. Example I will teach you. Okay, NO2, it's a monodentate ligand. At a time and one system, only 1 bond is formed with the central metal atom. True. But see here, you have nitrogen in NO2 and oxygen in NO2. So oxygen also has lone pair of electrons. Nitrogen also has lone pair of electrons. So both has lone pair of electrons. So the 1 bond that is formed with the metal atom, it can form through nitrogen also. It can form through oxygen also. So NO2, you can write it in 2 ways. One as NO2 itself, well, N has the lone pair of electrons, and you can write it as ONO minus, where minus is acquired on oxygen. So Ambidentate ligand is nothing but if a monodentate ligand contains two reaction sites, okay, two reaction sites, then it can bond through both the reaction sites at a time. So in one of the reaction, if it is bonding through oxygen, the other reaction it has to bond with nitrogen. But only one rule is that in one system it can bond either through one of the reaction site, either it can bond through oxygen or nitrogen. So if it bonds through oxygen in a system, it is said to be a nitrito ligand, and if it is bonding through the nitrogen, it is said to be a nitro ligand. So it has two reaction sites, but in one system it can react with only one coordination site. That is nothing but the ambidentate ligand. Similarly, thiocyanate. Okay, nitrogen also has lone pair, sulfur has also lone pair. So either it can bond through sulfur or through nitrogen. But the only condition is in one system it can bond through only one atom. So that is nothing but ambidentate ligand. So monodentate, one coordination bond; didentate, two coordination bond; polydentate, more than two coordination bonds; flexidentate, based on the requirement of the system. Polydentate ligands, okay, based on the requirement of the system, it will bond with how much ever coordination sites it's possible. Chelating ligand, if it is forming the closed structure, and ambidentate, if it's having the monodentate ligand is having a two different coordination sites. So this is regarding the ligands. Okay. Next we will talk about the coordination number. So I have given you here, we have talked about the ligand now. Next, we know what is central metal atom. Okay, now we have to talk about the coordination number. Okay, now there is major rule. Okay, there is major rule. Okay, there are three different types of ligands we will take. One is mono, bi, tri, okay, and polydentate ligand. Okay, polydentate ligand means how many coordination bonds are formed. Okay, if in the coordination sphere, if there is a monodentate ligand, okay, for example, what is an example of monodentate ligand? Cyanide. Take the example of cyanide is present, or water molecule is present. So what is, if a monodentate ligand is present, then the number of ligand, okay, the number of ligand is equal to the coordination number. For example, K4FeCN6, Cn is the monodentate ligand. So how many cyanide ions are there? 6 cyanide ions are there. So the number of ligand is nothing but its coordination number. So 6 cyanide ions are there. So since it is a monodentate ligand, its coordination number will also be 6. Next is bidentate ligand. Bidentate ligand means what? It can form two coordination bond at a time. So one ligand can form two bonds. So what it will be? The number of ligands into 2 will give you its coordination number. For example, oxalate C2O4, that is COO minus, COO minus. There are two coordination bond can be formed per ligand. So how many ligands are there here? 3. So each ligand can form two coordination bonds. So it will be 3 into 2, 6. So if it's a bidentate ligand, the number of ligands into 2. So that will give you its coordination number. Tridentate ligand. Okay. Tridentate ligand means it is having a 3 coordination sites. Then it will be into 3. The number of ligands into 3. Right. Similarly, further, for example, here take an example of this: COBr, NH3 twice, H2O thrice. How will you find the coordination number? See, H2O is monodentate ligand, so 3. Amine, again monodentate ligand, 2. Br is also a monodentate ligand. So you have to add up all these ligand numbers. So how many water molecule? 3 plus ammonia 2 plus 3 plus 2, it's 5. 5 plus 1, 6. So the coordination number will be 6. So for tridentate into 3, for tetradentate it will be into 4. Okay, based on how many coordination bond can be formed by a single ligand. So number of ligand into its coordination bonds. So that will give you the coordination number. Example, FeEn thrice. What is En? Ethylene diamine. So it's a bidentate ligand. So there are 3 ligands. Each ligand can form 2 bonds. So 3 into 2 it is 6. Amine, it's a monodentate ligand. So total number of ligand is 6. That will constitute you the coordination number. Carbonyl, it's again the monodentate ligand. So there are 4 carbonyl. So the coordination number will be 4. So that is nothing but the coordination number. So we have seen what is how to find the coordination number. Okay, what are the types of ligands? What are the types of complexes? This is regarding a vague idea regarding the coordination compound. Next comes the major question that is asked. One or two questions will definitely appear on this, that is the IUPAC nomenclature of a coordination compound. There are set of rules which I have to keep it in mind, okay, for why you name the coordination compound. So I have shortened the number of points so that quick points I have made, so that if you go through those points, you will be easily able to name the coordination compound according to its IUPAC nomenclature. First thing, whenever you see the coordination compound, you have to see, first you have to dissociate it and write. For example, K4FeCN6, if this compound is given to you, you have to dissociate it. If it is dissolved in the solution, how it will dissociate? So how it will dissociate K4FeCN6? It will dissociate as 4K plus FeCN6 3 minus, right? So you have got one cation and one anion. So what will be cation here? Potassium will be cation, and the coordination sphere is acquiring a anion, that is a negative charge. Remember, whenever you name, okay, the first, okay, you have to name the cationic species. Maybe it is a coordination sphere or ionic sphere, whichever, when you dissociate it, whichever gets the positive charge, that should be named first, followed by the anion. So in this species, which is acquiring a positive charge, ionic sphere is acquiring a positive charge. Your name should start with the naming of the ion, that is potassium, then followed by the coordination sphere. Okay. For example, in copper ammonium sulfate complex, when it dissociates, SO4 will get 2 minus negative charge and coordination sphere will get a positive charge. So which should be named first? The coordination sphere should be named first, followed by the naming of the anion. That is always, first point keep it in mind, cation should be named first, followed by the anion. That is the first rule of IUPAC nomenclature. Now, we have named the ionic sphere. We shall come to the naming of a coordination sphere. First, in the coordination sphere, always the ligand should be named first. So in the coordination sphere, there is two constituents, one is central metal atom part and one is ligand part. Always keep it in mind, ligand should be named first, followed by the central metal atom. Now in this, only one type of ligand is present. But here you can see there are more than one type of ligand. H2O is also a ligand, amine is also a ligand, bromine is also a ligand. So how will you name the ligands? Which will be named first? That is a question, right? So you have to name the ligands in the alphabetical order. For example, okay, this is aqua, this is amine and bromine. So these two are A, right? That should be named first, followed by the B, bromine. So based on the name of the ligands, okay, based on its alphabetical order, you have to name the ligands. First point is cation, then anion. In the coordination sphere, ligands followed by the central metal atom, and the third is ligand should be named in the alphabetical order of its name. Next, now some ligands will be negative in nature. For example, cyanide, okay, those are the negative ligands. Some ligands will be positive ligands, like for example NH4 plus. So for those kinds of ligands, there will be always a suffix attached to it. For example, okay, here there is bromine, right? It's a negative ligand, Br minus. It will exist as Br minus. It's a negative ligand, so it will have the suffix added to it. So if the ligand has the negative sign in it, it's always the suffix added to its name will be O, okay, or Edo. For example, it is cyanide, right? So you should attach O to the name of it, that it becomes cyanido. Similarly, chlorine, chlorido. So this is one example. Now the IUPAC name, for the recent IUPAC naming, it is not named as chloro, it is named as chlorido, right? So if the question in the options, if you have chloro, go for it, no problem. But according to the recent IUPAC naming, it is not chloro, it is chlorido. Similarly, bromine, it is named as bromido. Okay, if it's a negative ligand, it will end up with the suffix O. Cyanide, positive ligand. For example, not NH3, NH4 plus, ammonium. So what will be its suffix? It will end with IM, IUM, that is ammonia. Okay, it will end up with ammonium. So what is the next rule? If it's a negative ligand, it will end up with O as a suffix. If it's a positive ligand, it will end up with IUM as a suffix. But if it's a neutral ligand, for example, carbonyl, right? Ammonia, NH3, not NH4 plus, NH3 or H2O. These are the neutral ligands. So it will be having a special name, right? For example, NH3 is amine. Don't confuse, it is not AMINE. What is the name of it? AMM. This is a common mistake that is done. They only write amine. Okay, so you have to write double M. That is AMMINE. H2O. It is not written as water, it is written as aqua. Okay, if here you have to write triaqua. Okay, no need of adding any suffix, but it should be written as aqua, and NH should be written as amine, AMMINE. So these are the rules. Next rule is, okay, oxidation state. Okay, wait. Oxidation state. After you name a coordination sphere, okay, after naming the ligands, you have to name the central metal atom, right? You have to name the central metal atom. After you name the central metal atom, you have to write its oxidation state. So it is written in the common brackets. The oxidation state will be always written in the common brackets, but the oxidation state will be written in the Roman letters like this. So if it is having, the central metal is having the 4 oxidation state, it will be written in 4 Roman letters, not in normal numbers. So that is the next important IUPAC rule. Next, you have to name the central metal atom, right? After ligand, you have to name the central metal ion. In the starting itself, I have said you there are 3 complexes. Okay, if the coordination sphere is acquiring a positive charge, then it is a cationic complex. If it is acquiring a negative charge, it is an anionic complex. And if it is not acquiring any charge, it is neutral complex. So if your complex, if it is a cationic complex or neutral complex, the name of the, okay, central metal atom will be as it is. For example, here, okay, it is cationic complex, right? Cuprum, copper, 4 ammonia. This is a cationic complex because in the coordination sphere it is acquiring a positive charge. So while writing, you can write it as copper 2 complex. Okay, you can name it as just copper, right? But if it's an anionic complex, okay, if the coordination sphere is getting a negative charge, then ion, you cannot just write it as ferrum or iron. You have to write it as a suffix should be added, ATE, as you add O and IUM to the positive ligands, right? Similarly, if the metal atom is inside the anionic complex, then it should end with ATE. For example, for iron, it is ferrate. If it is nickel, it is nickelate. If it is Ag, it is argentate. So if it's an anionic complex, it should end with the suffix ATE. If it's a cationic or neutral complex, no need to add any suffix. It will be like that only. If it's copper, it will be copper. If it's iron, it will be iron. If it's nickel, it will be nickel itself. If it will be silver, it will be argentinum itself. Okay, it will not change. Only if it's an anionic complex, it changes to, it will have a suffix ATE added to its name. So what are the rules? First is cation should be named followed by the anion. Then we'll coming to the naming of the coordination sphere. First ligand should be named followed by the central atom, metal atom. While naming the ligands, you should see the alphabetical orders. You have to name according to the alphabetical orders. Okay. While naming it in the alphabetical orders, if there are negative ligands, it will have the suffix O added to it. If it's a positive ligand, it will have the suffix IUM added to it. And if it's a neutral ligand, there will be special name. For example, amine and aqua. Next, when you name a metal ion, if it's a cationic complex or a neutral complex, it will not have any special suffix. If it's an anionic complex, it will be having the special suffix ATE. Similarly, you have to mention the oxidation number and it will be always mentioned in the Roman letter, enclose it in the common brackets. Now we'll solve some of the examples. Okay, first CONH36Cl3. Okay, before
naming it, we should see how to calculate the oxidation number. That is also important. If you want to write the oxidation number of a central metal atom inside the bracket means we should know how to calculate the oxidation state of a coordination compound. So let us see that first. Okay, in this K4FeCN6, you have to see the oxidation state of iron. While you want to calculate the oxidation state of iron, you have to take in consideration the whole compound. Okay, so you don't know the iron oxidation state, take it as X. Okay, potassium, its oxidation state is +1. So how many potassium ions are there? 4. So what will be its +4 plus X? Okay, what is cyanide? It is -1. How many cyanide ions are there? 6. So what will be total oxidation number? It will be -6. So whole of the compound you will equate it to 0. So +4 plus X minus 6 is equal to 0. +4 minus 6 is -2. So X minus 2 is equal to 0, or X is equal to 2. So what is the oxidation state of iron in this compound? It is 2. Okay, +2 is the oxidation state. Similarly, next, chromium H2O6 times Cl3. You don't know what is the oxidation state of chromium. Okay, take it as X. Then H2O, you know that H2O and NH3 is a neutral ligand, no oxidation number for that, so take it as 0. Chlorine, you know that for any halogen the oxidation number is -1. Okay, so 3 chlorine atom is there, it is -3. So it will be X minus 3 is equal to 0, or X is equal to 3. So the chromium will be having the +3 oxidation state. Next, cobalt. Okay, CO, C2O4 is the oxalate, thrice 3 minus. Okay, for oxalate the oxidation number is -2. Okay, since there are 3 oxalate ion, it will be -6. We don't know what is X, take it as X, but equate not to 0 because the whole complex has some charge, that is -3. So X will become -3 plus 6, it will give you 3. So the oxidation state of cobalt in the complex trioxalato cobalt complex, it will be +3. Next is Fe En thrice Cl3. Again, okay, En, ethylene diamine, again it's a neutral ligand. Okay, so Fe, okay, +0 -3 is equal to 0. That is X is equal to 3. That is the oxidation state. Now you know how to calculate the oxidation state. Now try to name this compounds. Okay, so first compound CONH3 6 times Cl3. First rule, whatever comes into your mind, what is that? First, cationic complex should be named, followed by anionic. So in this, which is the cationic complex, the entity inside the coordination sphere, it will be a cation, and the outside chlorine, it will be anion. So start naming from the coordination sphere. Okay, when you name from the coordination sphere, what should be named first? Ligand should be named first. Okay, if the ligand should be named first, then you should say whether it is a positive, negative, or a neutral ligand. So which type of ligand it is? It is neutral ligand. So what will you write the name? You will write the name as AMMINE. So how many ligands it is? Hexa. So hexamine, right? Ligand is named. Then you have to see it is a cationic complex. So no need of adding any suffix ate to it. So you have to write it as cobalt itself. So hexamine cobalt. So what is the oxidation state here? Count. Okay, chlorine -3 plus ammonia is 0. X minus 3 is equal to 0. So X will become 3. So what is the oxidation state of cobalt here? It is 3. You have to write it in the Roman letter 3. Now outside it is anionic species. Okay, you have to write it as chloride. Okay, it's coming out of anion, right? It's nothing but you have to write it as chloride. So the name will be hexamine cobalt 3 chloride, right? Next, KPTNH3Cl5. Okay, if you dissociate it, the coordination sphere, it will be anion, and outside it will be cation. So always first we have to name the cation. So we'll start with the ionic sphere. So write it as potassium. Okay, potassium. Next, we'll come to the coordination sphere. There are 2 ligands now, right? 2 ligands. So which comes in the alphabetical order. Amine comes first, then chloride. Okay, what type of ligand is amine? It is a neutral ligand. So you have to write it as what? Once again, you have to write it as A-double-N. Yes, so I have missed here, right? So there is a mistake here. It should be A-double-M-I-N-A. Okay, potassium amine chloride. Okay, it's a negative, right? Negative ligand. So what it will become? It will have the suffix O. So it's 5-chlorine, pentachlorido. Then comes central metal atom. Since it's an anionic complex, what should be the suffix for the central metal atom? It should be ATE. So it is platinate. What is the oxidation state? If you calculate, you will get the oxidation state 4. So you have to write in brackets 4. So it will become potassium. Make it correction here. It is double MINE. Potassium amine pentachlorido platinate 4. So this is the IUPAC naming of the given molecule. So these two examples have solved here. So using these series set of rules, you can solve. If any compound is given to you, you can easily write its IUPAC naming. And also if they ask you to calculate the oxidation state, you can easily calculate. So this is regarding the coordination compound. Okay, this is the first part. Then we will go to the isomerism part. Okay, so this is one of the major. So isomerism. Okay, when you are taught, there is a famous types of question that is asked in each of the KCP exam. Each year it is asked. They will give you a compound. You should tell how many isomers are possible for that particular compound. Okay, isomers, when you are talking about, there are different kinds of isomers. So the main classification is structural and stereoisomers. In structural isomerism, there are 4 types, and in stereoisomerism, there are 2 types. So how many isomerism you have to look into for a particular compound? 4 structural isomers and 2 stereoisomers. So the main question they will be asking is, they will be giving you a compound and they will ask you how many isomers are possible for that particular compound. To answer that particular question, you have to keep in mind what are the types of isomers, how to identify a particular isomer in the compound. So that we'll be discussing here. Isomers, there are 2 major classification of isomers. One is structural isomers and second one is, this is geometrical, okay, this is called a stereoisomer. So in structural isomerism, there is 4 types. Okay, what are those? We will see. The first type is ionization isomers. Okay, for example, take this as an example. Here it is given as cobalt, okay, tetraammonium, chlorine and bromine is in the ionic sphere. Here you can see cobalt, 5-ammonia, bromine is inside the coordination sphere, whereas chlorine is outside the coordination sphere, or it's in the ionic sphere. Ionization isomers are nothing but 2 compounds with same molecular formula. Check the molecular formula in both the compounds. It is C1O1, right? N5H15 ClBr. Similarly here C1O1 N5H15 Br and Cl. So the molecular formula is same. So the number of particular constituent atom is same. But what is differing here? When these individual components ionize in the solution, what happens? The ions that will come out are different. In this compound, the ions that is coming out is Br minus individually, whereas here it is Cl minus. So 2 compounds have the same molecular formula, but ions that is coming out of the ionization is different. Or in other words, the ions that are present in the ionic sphere is different compared to that of a coordination sphere in these 2 compounds. Those isomers are said to be ionization isomers. After ionization, the ion coming out individual, it is different in both the compounds. Okay, whereas the molecular formula is same, right? That is nothing but the ionization isomerism. Second is hydrate isomerism. Now, again, in both the compound, the molecular formula is same, but the number of water molecules inside the coordination sphere Okay, if it should be inside the coordination sphere means it should act as an ligand. So the number of water molecules acting as a ligand is different in both the compounds. You can see here in this 6 water molecule will act as a ligand in this compound, whereas the 5 water molecule will be acting as ligand and 1 water molecule is outside the coordination sphere. It is not acting as a ligand. It is there in the compound, but it is not acting as a ligand, or it is not inside the coordination sphere. But when you are talking about the molecular formula, it is Cr1 H2O6 Cl3. Similarly, Cr1 H2O5 plus 1 6 Cl also 1 plus 2 3. So there are same number of molecules, but the number of water molecules acting as a ligands inside the coordination sphere is different. One is 6 ligands is water molecule and 5 ligands is water molecule in the other compound. That is nothing but the hydrate isomers. So second isomer. Third is linkage isomers. You have studied what is ambidentate ligand. In same ligand, there will be 2 reaction sites. At a time, only one reaction site can act as a bonding site to the central metal atom. Same thing here. Here, if NO2 is present in both the compound, right? Okay, if you write the molecular formula, it will be C1, right? O3 again. Here C1, O3 again. Nitrogen is 5 plus 1, 6. Again, nitrogen 5 plus 1, 6. Okay. And hydrogen it is 15, hydrogen it is 15, chlorine it is 2. The molecular formula is same. It may be termed as an isomer. What is the difference? Here in this NO2, when it is acting as a ligand, you can write it as nitro. Why? Because oxygen is acting as a reaction site. Whereas here, nitrogen is acting as a reaction site here in the NO2, whereas in ONO, nitrito, oxygen is acting as a reaction site. So there is a difference in the linkage, okay, in from which atom the coordination bond is linked to the central metal atom. That is the difference here. That's why it is classified under linkage isomer. Same molecular formula, but because of the ambidentate ligand present, the reaction site, it is different in both the compounds. That is nothing but the linkage isomers. The last structural isomer is coordination isomers. Okay, there is 2. One is ionic sphere, one is coordination sphere. The molecular formula in both the compound is same, but the ligands in the coordination sphere is different. Here, okay, amine is the ligand. Okay, NH3 is the ligand inside the coordination sphere, whereas the cyanide is the ligand here. When you see the molecular formula, it is same, but the ligands inside the coordination sphere, that is forming the coordination bond, it is different. In one it is amine, in one it is cyanide. So different ligands take part in the coordination bond. When you overall consider a compound, the molecular formula is same, but the ligand that is participating, it is completely different in both the compounds. That's why it is said to be a coordination isomers. Coordination because the ligand that is responsible in forming the coordination compound inside the sphere, it is completely different. So 4 types of structural isomers. One is ionization isomers, differ in the ions coming out in the solution. Hydrate isomer is number of water molecules acting as a ligand. Linkage isomerism, reaction site, and coordination isomerism, different ligands. So these 4 are the structural isomers. Okay, possible. Next comes stereoisomerism. I have not mentioned here. In stereoisomerism, there are 2 types. One is geometrical isomerism. Once again, one is geometrical isomerism. And second one is optical isomerism. Okay. First, we will see what is this geometrical isomerism. They are called as cis-trans isomerism. For example, there are 3 types of complexes, namely, right, based on how many ligands are responsible. Okay. One is square planar complex. Okay. 4 different coordination bonds, square planar complex. Second is tetrahedral, right? 1 will be at the top and 3 will be at the bottom. So that is tetrahedral. And third one is octahedral. Okay, 6, right? 6 coordination bonds will be there for one particular atom. Okay. Now, based on if the same two ligands are on the same side of the plane, then it's said to be a cis isomers. I'll tell you with the example later. And if those two same ligands, for example, there are Cl2, 2 chlorine, okay, if they are on the same side of the plane, they will be said to be cis. But if they are in the opposite space, like as a mirror image, okay, if they are there, then it is said to be a trans isomer. So general name of geometrical isomer is cis and trans isomers. Now, there are three types of complex: tetrahedral, square planar, and octahedral. Always remember, if they give you any tetrahedral complex and if they ask you how many geometrical isomers are possible for the tetrahedral complex, you can directly write it as 0, because that is a shortcut what I'm saying. That is nothing but tetrahedral complexes do not show geometrical isomers. Why? Because even 1 is at the top and 3 is at the bottom, all 4 ligands lies on the same plane. Okay, all 4 ligands lies in the same plane. So there is no possibility of trans and cis isomers in them. Okay, because other side of the plane the ligands will be empty. So you cannot compare. So if the tetrahedral complex is given to you, you can directly write that tetrahedral complex do not show any kinds of geometrical isomerism. It will not show cis trans isomerism. Now, second, what is 4 ligands? It is square planar complex. Okay, you can write, okay, different square planar complex. For example, you can see here, M is the central metal atom, Ma2X2 type, where you have 2 types of ligands. So 4 bonds should be filled. You know, central metal atom, we can take an example of Pt. You have 2 different types of ligand. One is chlorine here, one is amine here. Okay, A2X2. So each of these ligands are 2 in number. That is Pt, NH3 twice, Cl2 twice. Okay, here cis and trans isomerism is possible. Why? Okay, you can write platinum will be in the center, ammonia, ammonia, chlorine, chlorine. So if you divide the plane in between these 2 ammonia, they can be on the same side, cis isomer of ammonia. Similarly, if you position 1 ammonia here, 1 ammonia here, it is the trans isomerism. Similarly, with respect to chlorine, you can write cis and trans isomerism. So in type Na2X2, cis and trans are possible. So geometrical isomerism is possible. Next, MAbX2. 3 types of ligands are there. For example, Pt, ClBr, ammonia. But one of the ligand is 2 times. Okay. In this case also, with respect to ammonia, you can write cis and trans isomer. Okay, cis and trans isomer. Next, A comes Ma2Xy. A2 here it is Aa2. It means you are taking didentate ligand. You know that in didentate ligand, 2 sides, okay, at a time 2 bonds can be formed. So 2 of the out of 4, 2 coordination site is acquired by 1 didentate ligand and chlorine, bromine. Here also you can write what? Cis and trans isomers. Similarly, 4th one. Now this is a confusion. Okay, they have given that. I will tell you that A, B, X, Y. All 4 ligands are different, but still you can have cis and trans isomers. How is that possible? Take an example of chlorine, bromine, ammonia, and Py. Now, what is chlorine and bromine? Both are halogens, right? And these are different. So, if you elaborate it and write, let us write it like this. Okay. M, you will write it in the center. A, B, X, Y. Let us take 4 different. Now, fix one position, okay? Fix the position of A. Don't move it, okay? But interchange these 3 ligands, okay? In the second, how you can write A, fix the position of A. In place of B, you have written Y, okay? In place of X, you have written B. And in place of Y, you have written X, right? This is the second change. Again, fix the position of A. Now, again interchange it. In place of Y, X has come. In place of B, Y has come. In place of X, B. Only these 3 different arrangements you can make, right? Again, if you make the arrangement, you will come at the first structure itself. Now, if in that series MAbXY, if 2 of the ligands are of the same family, for example, here ClBr, they both are halogen, they act in the same way. If you compare those 2, you can write cis and trans isomer. For example, A and B, compare it as Cl and Br, same family, right? they are on the same side, cis isomers. Here again, they are in the opposite side, trans isomerism. Again, they have come closer, that is cis isomerism. So for MABXY, condition is any two are of the same family. You can have two cis isomerism and one trans isomerism out of it, right? In square planar complex, okay, MA2X2 shows cis and trans isomerism, MABX2 shows cis and trans isomerism, MA2XY, where A is the bidentate ligand, it also shows isomerism. Similarly, ABXY, it shows two cis and one trans isomerism. If any compound is given to you with all four ligands different and two are of the same family, they ask you how many geometrical isomerism are possible. You can directly write two cis and one trans, total 3 isomers are possible for such type of compound. Now, we have seen these 4 types of complexes show cis and trans isomerism. Which are the complexes in square planar that will not show you the cis and trans isomerism? First one is Ma4. All the ligands are same. For example, FeCl4, right? All 4 are chlorine complex, chlorine ligands. It means you cannot change. All 4 will be in the same plane. At a time, all 4 will be in the different plane. So you cannot write cis and trans isomerism. Similarly, one ligand is different, rest 3 are similar. Like for example, you can write FeBrCl3, 3Cl, okay? You can write cis, you can't write trans, right? Similarly, those do not show what? Cis and trans isomerism. Similarly, other way around. Okay, here MBr3Cl, okay? 3 again it is similar and 1 it is different. They also do not show what? Geometrical isomerism. So which kind 4 show? You should know in square planar which 4 types will show cis and trans isomerism and which 3 are that do not show cis and trans isomerism. So that is a shortcut which I have given to you. If you see the compound of this type, you should directly see how many isomers are possible for that, whether it is showing geometrical isomerism or not. This is a shortcut. First, if a tetrahedral complex comes, say that directly 0 isomers or geometrical isomerism are possible, right? If square planar complex comes, you have to see which is the type of compound it is given. Based on that, you have to judge whether geometrical isomerism are possible or no. Next comes octahedral complex. Octahedral complex means what? Central metal atom is surrounded by 6 ligands, right? Now, what will be the cis position? Cis means what? 2 of the ligands should come on the same side. Now, okay, take this as a plane. Okay, take 1M4 as one plane. Okay, then what are the cis positions you can write? 2 and 3, 6 and 5. Right? 2 and 3 is similar to 6 and 5. You can write as 2 and 3. Then take 6M3 as the position. Then 1 and 2. Right? 1 and 2. Next, take M52 as the position. 3 and 4. Then 6M3 as the position. 4 and 5. 1 and 2 and 4 and 5 is still same, but there will be slight difference. I'll tell you what. So the cis position are 1 and 2, 2 and 3, 3 and 4 and 4 and 5. Rest it is same. Next, transposition. What is the transposition here? See, with respect to this 1 and 4, right? 1 and 4, 2 and 5 and 3 and 6. Those are the transpositions. So totally 4 cis positions and 3 transpositions are possible for a octahedral complex. Now type 1, MA4B2. What do you mean by MA4B2? 4 are the same ligands and 2 are different ligands, that is COCl2 NH3 4 times. Again, you can write cis and trans isomers. Similarly, MAA twice B2. AA means En, one bidentate ligand. Okay, AA twice. How you can write it as? Here En if it is there. Okay, these 2 sides will be occupied by one En. These 2 sides will be occupied by other En. Right? You can write trans isomerism for that. So if you write 1 and 2, so here one En and here one En, it will be cis isomer, right? Similarly, chlorine. With respect to chlorine, you can write chlorine in the opposite, chlorine on the same side, right? So that will give you a cis isomer. Type 3 is MA3B3. MA3B3 means 3, 1 ligand. 1 second. 3 one ligand and 3 other ligand. So that also can show cis and trans. But remember, in octahedral complex, cis isomer is said to be a facial isomer. They can ask you how many facial isomers are possible. Okay, cis isomers means facial isomer is MERS. It is also written as facial isomers, and trans isomers, the equivalent word is meridional isomer. So type 1 is MA4B2. Second one is MAA2B2, that is didentate ligand is involved. Second one is, third one is MA3B3. These three types of isomers show octahedral complex. How many cis positions? 4 cis positions and 3 trans position of octahedral compound. So this is regarding the geometrical isomers. Okay, in stereoisomers, in geometrical isomers, tetrahedral complex do not show geometrical isomers. Square planar complex 4 show and 3 do not show. In octahedral complexes, 3 are the types of compounds which show what? Cis and trans isomers. The equivalent name for cis is facial isomers and equivalent name for trans is meridional isomers. Now comes optical isomers. Second one is optical isomers. Okay, what is the difference between geometrical and optical isomers? When you talk about it, so geometrical isomers are possible because there is a symmetry in the molecule. For example, if you take an octahedral complex, this is a symmetry, this is a symmetry, this is a symmetry, right? There is a symmetry in the molecule. Similarly, in square planar, there is a symmetry in the molecules with which the ligands are arranged around the central metal atom. In optical isomerism occur due to the lack of symmetry. So there is no symmetry in the complex. Okay, if there is no symmetry in the complex, it has optical isomers. Okay, one condition is lack of symmetry. Second one is they should be non-superimposable mirror images of each other. If you cut the molecule in half, the two halves, okay, if you superimpose, it should not be the mirror image. It means same ligand should not superimpose on the other half. One half, it contains Cl and Br. The other half, okay, it should not contain Cl and Br, because if you put one half on the other half, it should not superimpose. It should not be of the same ligand. So that is the condition. That is, two isomers are non-superimposable mirror images of each other. Two compounds, if you superimpose on one another, okay, it should not coincide with each other. That is the condition for optical isomers. Since you name geometrical isomers as cis and trans, here you name optical isomers. One is dextrorotatory, that is D isomers, which rotates the plane polarized light to the right side, and second one is levorotatory, that means L isomers, which rotates the plane polarized light to the left side. Similar to cis and trans, in optical isomers you have D isomers and L isomers. We'll see with an example. Okay, there here square planar does not show what geometrical isomers. Why? Because there is a symmetry. Similarly, tetrahedral also do not show what optical isomers, but only octahedral complexes show optical isomerism. So if they give you a tetrahedral complex or a square planar complex and tell you to identify the optical isomers present in it, you can directly write 0 isomers. Why? Because tetrahedral and square planar do not show optical isomerism. Don't confuse. In geometrical isomers, tetrahedral do not show. In optical isomerism, square planar and tetrahedral both do not show optical isomerisms. Okay, now let us take an example here. For example, okay, COCl
Cl2En twice plus complex. Okay, Cl2En twice. How you can write this? Okay, 2. Okay, one is E, 2 means 4 coordination site is occupied and 2 other is occupied by Cl2. It means it is an octahedral complex. 6. Write it now. CO. Write Cl2. Okay, these 2 sites it is occupied by 1 and these 2 sites is occupied by 1, right? Okay, this is cis isomers. Why? Because En is on the same side, Cl is on the same side. If you write the geometrical isomerism, trans isomerism, how you will write? CO, Cl, Cl in the opposite direction, En, En in the opposite direction. Okay, since in this to the optical isomerism, you should know you should not have symmetry. Okay, in this, do you have symmetry? Yes. So one cis you can write and one trans you can write. Always remember, in octahedral complex, cis complex is always optically active. Why? It is experimentally found example. Okay, when a plane polarized light, when a cis isomer is passed to the plane polarized light, it changes the direction of the plane polarized light to the right side. That's why cis isomer of any octahedral complex is active, whereas the trans isomer is inactive. So if they give an octahedral complex, so if they tell you which form is active, you should write cis form is active, optically active, whereas trans form is optically inactive. Similarly, if you write COEN thrice plus 3, okay, COEN thrice. Thrice means what? 1, 2, 3. All it is same. Again, you can write cis and trans. Cis is active, trans is inactive. Similarly, CrC2O4 thrice 3 plus. Again, cis is active, trans is inactive. In octahedral complex, what? Cis is optically active and trans is optically inactive. So we'll see, now we have seen what is geometrical isomer, what is optical isomer, and what is structural isomerism. We'll see some of the questions that has appeared in last year question papers, okay, on isomerism to make you clear. The first question is, so I have told you this kind of a question will appear. How many stereoisomers are possible for complex? The given complex is CrCl2, OX means C2O4 twice 3 minus. They have asked you stereoisomer. What is stereoisomers? Stereoisomers are nothing but what? Geometrical isomers and optical isomers. So you have to only think geometrical and optical isomers. So which complex is OX2Cl2? It is octahedral complex. So does octahedral complex show optical isomerism? Yes. Okay. Yes. Right? It shows optical isomerism. But in optical isomerism, in cis and trans, which will be optically active, only one form is optically active. So one optical isomer it shows. Yes, correct. Geometrical. Now this is an octahedral complex. It is of the form what? It is MAA2B2, right? See, I have given MAA2B2. How many isomers you can write? Okay, one cis and one trans. You can write one cis and one trans. So two geometrical isomers are possible and one optical isomerism are possible. Total 2 plus 1. Total amount of stereoisomers that are possible is 3. That is the answer. Okay. Second question. The one that will show optical activity, they have given you the 4 molecule, okay, which will show optical activity, which is a type of a complex. It is an octahedral complex. We'll check, which is obvious. Okay. Optical activity. Optical activity, when you are seeing, you will see the symmetry, right? First, see this complex. Does it have symmetry? Yes. When you cut along this, when you impose, when you join the two halves, it is superimposable. The main idea for optical isomers is it should be non-superimposable mirror images. It is superimposable, so it's not possible. Next, in this, we cut this half. Okay, these two are again superimposable mirror images. Again, this cannot be. So B and D option is ruled out. Now the confusion here. So in both, if you quit, they are non-superimposable mirror images. But which is there? So I have said you AB and BA.
right? AB and BA. C, on this side also same ligand, A and B is present, and this side also it is same ligand, B and A. It may be positioned on the top or in the bottom, but when you superimpose, they coincide, right? Because same ligands are there on the same side. Here also the ligands are AB, here also ligands are AB, but they are positioned in a different way. Still, they will be superimposable mirror images when you cut along these sides. Okay, so it also ruled out this also cannot be optical isomerism. This is obvious choice because when you fold across this side it is EN and this side it is other ligands, that this will be the one which will show optical activity. Why? Because it is not having symmetry, and if you cut across the line it is non-superimposable mirror images. Okay, so next question. So see, the total number of isomer for square planar complex. Okay, sorry. The total number of isomers for this square planar complex. This is a square planar complex MFCl SCN NO2. This is square planar complex. Total number of isomers. They have not asked you structural or stereo. They have asked you total number. So which all isomers you have to consider? 4 structural isomers, right? 2 geometrical isomers and 1 optical isomers. You know that first you rule out which is obvious to you. So you know that square planar complex do not show what? Optical isomer. So no optical isomer. Rule out the optical isomer point in that. Next comes geometrical isomers. Yes, geometrical isomer. What is the type of a square planar complex? It is MABXY. All 4 are different. But fluorine and chlorine, what is it? It is same family ligands. So if there are 2 same family ligands and all 4 ligands are different, how many cis and how many trans isomers? 2 cis and 1 trans isomers, right? 2 cis and 1 trans isomer. 3 isomers are there, right? 3 so already done. 2 cis and 1 trans, 3 isomers. Now come to structural isomers. Does it show ionization isomers? No. Why? Because none of the ion is outside the coordination sphere, right? So ionization isomer is ruled out. Next, it comes hydrate. No water molecule, no hydrate isomers. Coordination, okay, no 2 spheres there, okay, to see coordination isomers. But linkage is there, right? 2 linkage ambidentate ligands are there. One is nitro, one is SCN, right? So with respect to 1 nitro, right? For nitro, 2 isomers are possible, right? You can write with ONO and you can write with NO2. And for SCN, 2 isomers. You can write donate from S and donate from N. 2 linkage I2 isomers, that is the linkage isomers of SCN, and 2 isomers for NO2. And each of these 2, okay, this is total 4, right? And each of these isomers will form 2 cis and 1 trans, right? 2 cis and 1 trans. So it is 4 into 3, total 12 isomers are possible. 2 isomers because of ambidentate SCN ligand, 2 isomers because of nitro ligand, and each of these 4 isomers will form 2 cis and 1 trans with respect to each other. That's why total isomers here is 12. So the answer here is 12. So these are the type of questions they will be asked. They'll ask you regarding the isomer. So this is the lecture 1. We will see rest of the theory, that is Werner's theory, BBT and molecular orbital theory. We will cover in the next lecture series. Okay, this is regarding. So in today's class, we have studied what is coordination compound, how is coordination compound different from the double salt. Okay, what are the components of the coordination bond, that is from the coordination sphere, what is ligands, types of ligands, okay, then what is coordination number, how to calculate the coordination number, how to name a given compound, how to find its oxidation state, what are isomers, different types of isomers. Structural we have studied 4, in geometric, in stereo we have studied 2, that is geometrical and optical. Shortcuts I have told you which types of complexes show what isomerism, and we have discussed some of the problems. So this synopsis is enough for you to brush up regarding these concepts in the coordination compound.